And so our first speaker for today is Kiyoshi Ramani. He's going to talk about CLOTHO, a tool for detecting serializability violations in database systems.
Thank you so much. Good morning, everyone. I'm Kiyoshi Ramani, as was mentioned. I'm going to present my joint work paper, which was done by me, Dr. Kartik Nagar, Dr. Benjamin Delaware, and Dr. Suresh Jagannathan, all from Purdue. I'm a PhD student here. In this talk, I'm going to briefly present the background and then explain the problem that we're tackling in the paper, and of course, go through the details of the solution. And lastly, share some empirical results that we were able to collect in our evaluations of the solution. So traditionally, database applications have been considered to be consisted of a set of logically independent units of work, named transactions, which work with data, highly structured data stored in the database. These programs are executed by spawning new transactions following client requests. And transactions can send arbitrary data retrieval and modifications to the databases, which are then processed there and returned with some possible set of results. Databases historically have offered a set of guarantees to these programs, which have been collectively referred to as ACID guarantees. ACID is an acronym where A stands for atomicity, meaning that transactions should execute it in their entirety. They should either commit in their entirety or should not commit at all. C stands for consistency, meaning that each transaction must witness only a single copy of each data item. Isolation specifies that transactions, even if they are executed concurrently, must not witness each other's presence. And lastly, durability specifies that modifications done by a committed transactions should be stored in the database permanently. In this paper, we focus on the first three of these guarantees, which are also referred to as serializability guarantees. Serializability facilitates program design and reasoning. For example, consider this very simple application execution, where the database includes only a single table with two columns, a customer ID and customer payment count. And two instances of the same transaction are spawned, which perform a very simple task. They retrieve the record, increment the value, and rewrite a fresh value into the database. It is extremely easy to understand how this program would be executed when serializability is offered. Select reads value 50, update writes 51, the database state is updated. The next select reads 51, the next update writes 52, and the final state of the database is 52. It is in fact quite easy to argue about any execution of these transactions against serializability and say that, for example, in the value of customer payment count in the final state of the although serializability guarantees are quite attractive for program design and analysis, they are extremely costly to enforce in practice. And as a result, a weaker set of guarantees, collectively referred to as weak isolation and weak consistency guarantees, have been introduced. Weak isolation guarantees, as you might expect, means that allows transactions to be executed concurrently, even if they witness each other's presence. And similarly, weak consistency guarantees allow database systems to maintain multiple copies of the data in possibly geographically distributed locations, which are only loosely synchronized. In such a setting, an execution like this would be possible. For example, a transaction is spawned, an update goes to the first replica, then subsequent select goes to the replica 2, which, however, does not witness the effect of its own update because the two replicas are not synchronized yet. As we kind of already witnessed, when guarantees of serializability are not offered, programs can show unexpected behaviors and reasoning about them becomes non-trivial. For example, the same two transactions that we just witnessed their execution, if they're executed in a weakly consistent and isolated environment, could be executed like this. The first select could read 50, the second select also could read 50, and both updates would write 51, leaving the final state of the database at 51. Which is an invalid final state of the execution based on what we expected when we spawned these two instances of the transaction. These unexpected behaviors, however, must not be taken lightly. In fact, a recent study by researchers at Stanford University found that similar unexpected behaviors could be exploited by attackers to perform unjustified financial transactions in an online shopping application, which could potentially put over 2 million websites, including these famous ones, into potential financial danger. So what should we do? So application developers must carefully study and analyze every application that they design in order to find these unexpected behaviors, which I'm going to refer to as serializability anomalies from now on. However, these serializability anomalies tightly depend on the structure of each application and also the set of behaviors that the underlying database system allows, meaning that developers now have to extensively test each application against any database system that they might want to use in production in order to find such cases. And to make the matter worse, each of those database systems themselves might offer various degrees of consistency and isolation semantics, making the testing even more time and resource consuming. But even putting the consumption of time and resource away, testing fundamentally is not a reliable way to finding the set of all serializability anomalies, which could be crucial, especially if sensitive data is involved. And that is not surprising, considering the huge space of concurrent executions that programs can go through. Only a few of them might trigger a serializability anomaly. To be more precise, in order to trigger a serializability anomaly, one might have to determine the initial state of the database, the exact execution path each transaction takes inside, the arguments that transactions are provided with, the exact ordering between the interleaved operations from concurrently running transactions, and last but not least, the exact timing of possible partitioning that might occur in the replicated setting of multiple copies of the data. So, meaning that testing is not a reliable way to find all such anomalies. So what should we do? In this work, we try to ask an alternative question. So instead of whatever we just discussed, what if we logically encode these interesting database applications and the set of executions that they are allowed to perform in order to facilitate a symbolic and efficient search of the state of executions against particular consistency and isolation semantics of a particular database. And the next question is that, can we make the encoding precise and rich enough that we would be able to map any found anomaly in that model back to executions of the actual application and execute them against the actual database and witness them and study them and analyze them? The answer turned out to be yes. In this paper, we developed CLOTHO, which is an end-to-end automated directed testing framework for applications of weakly consistent and isolated databases. CLOTHO is consisted of two main parts: the static analyzer, which is the purple box, and the replaying mechanism, the yellow box. The static analyzer part of the CLOTHO, given an application, through a logical encoding and communication to an off-the-shelf SMT solver, creates a set of abstract anomalies, each of which could be used to create instances of the original program, which are annotated with necessary information about the ordering of operations and networking partitioning, and also are accompanied by an execution schedule, which would lead those instances to manifest an anomaly. These instances and the execution schedule are then passed to the replaying mechanism, which would execute those applications according to the order specified in the execution, and if necessary, would also create artificial partitioning in the between the nodes of the replicated database that these transactions are being executed against. So let's go through the pipeline of CLOTHO using the example that we already operations in AR are still maintained. For example, in this example, I'm sorry if it's not visible, the first operation retrieves a set of records and stores them in V, a variable V, which is accessed by the next operation through function proj, which projects the value in the C payment count column of the first row stored in variable v. So these transactions in AR are then passed to the encoding engine, which will create an FOL encoding of the problem that we have through a process that I will explain shortly. And through communication to an SMT solver, creates anomalies which would allow it to create these annotated instances of the original program. As you can see, hopefully, these annotated instances provide these transactions with concrete input and tag each database query with their relative order in that transaction and the database node that they should be dispatched to. As I mentioned, there is also a schedule provided at this step which would tell the replaying mechanism what order these queries should be executed. For example, in this example, it is specified that the first two select should go first and the two updates should go next in order for this anomaly to be manifested. Additionally, the execution schedule also includes any database row which must already exist before these two transactions are executed. For example, in this case, it is specified that a customer record must exist in the database in order for these values to retrieve and update it. Moving on, so I'm going to briefly explain the operational semantics in an informal way of CLOTHO, using which I will formalize the notion of serializability anomalies, and that will clarify how we find serializability anomalies in a given application in a static way. So applications in CLOTHO are executed by choosing an arbitrary operation and dispatching it to an arbitrary partition. When operations are executed in a partition, a set of read or write effects are created, which capture the intended behavior of that operation. And their value depends on the set of effects that are already present in that partition. In order to concisely capture the concurrent execution state of programs in CLOTHO, we also had to define two additional relations between effects, namely arbitration order, which offers a total order between effects created in all partitions, and visibility order, which is more refined and only relates to effects if one causally precedes the other, meaning that only the set of effects that are present in a partition are made visible to an effect which is newly being created there. For example, consider this execution state where two transactions are spawned and are executed against two partitions. Assuming that the first one goes to partition 1 and the rest go to partition 2, and they are executed according to the order that they are tagged with, this would be the arbitration order between these effects and the transitive closure of these edges, of course. And this would be the visibility edge between them. As you can see, visibility does not relate the effect of operation 1 because it was in another partition and was not causally preceding effects in the partition 2. So now that we have defined how executions move forward in CLOTHO, we have to formalize what serializability anomalies are. In order to do so, I have to first define a set of dependency relations between operations. The first dependency relation is write dependency, or WW, which relates to operation instance if both create write effects to the same object. The next one is read dependency, or WR, which relates to operation instance if one creates a read effect which witnesses the write effect created by the other one. For example, here, the select witnesses the effect created by update, hence the WR established between them. The third one is RW, or anti-dependency, which relates an operation if the read, relates to operations if the read effect created by one does not witness the write effect created by the other, but if it was witnessing it, the value of the record would be different. For example, in this case, the select operation has an RW relation with the update because the effect created by update is not visible or witnessed by the select. And lastly, there's an SD edge which simply relates operations that are from the same transaction instance. We can take this further now and define dependency graphs given an execution. Dependency graphs is simply defined as a set of all dependency edges between all operations that reside on an execution. And using this, we can claim that an execution is serializable only if and only if its dependency graph does not include a cycle. Alternatively, we can think about it this way. Finding serializability anomalies is now reduced to constructing a concurrent execution, the dependency graph of which includes at least one cycle. All right, so for example, consider again the same application, the same transaction. As we witnessed before, the two spawned instances of this transaction could be involved in a serializability anomaly. Indeed, if they are executed in this order, selects go first, updates goes next, there would be these RW edges between them, creating a cycle, meaning there is a serializability anomaly between them, which is in accordance with what we observed before as well. So now moving to the FOL, the encoding engine of CLOTHO. Given an application, the encoding engine of CLOTHO creates FOL constructs for each operation type and transaction types and allows arbitrary instantiation of them. It also creates the relations that I just described, visibility, W on RW, using which in CLOTHO, we have been able to show that the problem of finding a bounded serializability anomaly in a given program can be reduced to finding a satisfying assignment to a formula, namely phi c. Phi c itself is consisted of 5 conjuncts. The first one, phi context, simply specifies a set of constraints on that any valid execution of any valid database should follow. I'm going to skip that. Phi db includes a set of user-defined constraints on any state of the database. For example, they could specify that all the records in the database must be above 21 years they must be 21 years old at least. But more interestingly, users can also add any specific consistency or isolation semantics offered by a particular database into the encoding in phi db. In CLOTHO, we have shown that many of famously offered isolation and consistency guarantees could be concisely specified as constraints on the visibility relation in an execution. And by adding these constraints in the encoding, the SMT solver would now wouldn't generate spurious executions which are not possible to happen, which are not possible to be replayed in the actual database under test. The next conjunct specifies a set of necessary conditions to establish a dependency relation. It is defined through a set of conjuncts which specify that if a dependency relation D holds between two operations, it must be the case that a set of propositions also hold between them. These propositions are defined through a set of rules in the paper based on the operations involved and the dependency edge between them. For example, in this example, for instance, in this rule, the set of necessary conditions in order to establish an RW relation between a select and update are defined as follows. It specifies that there must be a record in the database that satisfies the where clause of both queries, meaning that both queries should be able to access it, and should be alive, meaning that it must be in the table at the time that those queries access the database, and both of those queries should be accessible in the control flow of their corresponding transaction at the same time. The next conjunct, very similarly, defines a set of sufficient conditions in order to establish a dependency relation between two operations. Again, a set of conjuncts are defined, specifying that if a set of propositions hold between two operations, then a dependency edge between them must also hold. Again, these propositions are defined using a set of rules in the paper based on the operations involved and the dependency edge. This is very similar. It just specifies that, if an update operation is visible to a select, and there is a row that they both access, and it is alive, and they are both accessible in their control flow of the transactions, it must be the case that there is a WR between these two operations. The last conjunct, phi anomaly, is parameterized over three variables, I, J, and K, and itself is consisted of 3 conjuncts. The first conjunct forces the SMT solver to instantiate I transactions which are executed serially. The second conjunct forces the SMT solver to instantiate J transactions which are executed concurrently, but manifest a dependency cycle of length k between them. And the last one simply specifies that all the serially executed transactions must be committing before these concurrent transactions. The existential quantifier in this formula can be thought of as the core of the queries that we send to the SMT solver. The rest of the formulas that we have defined so far could be thought of as additional constraints that are specified in the set of solutions to this particular formula. And also the parameters I, J, and K could be used to design a systematic search algorithm on the space of all possible anomalies within a certain bound. In fact, in CLOTHO, we have designed a search algorithm which takes as input maximum values for each of those variables, and is constructed of two parts. The first part tries to find all cycles within the specified bounds that could occur in any concurrent execution of the program. It does so by constructing the phi cycle formula, which I explained earlier, and sending the query to the SMT solver. Any satisfying assignment to this query is then added to the set of solutions, the negation of which is also added to the encoding to make sure that two identical cycles are not returned in two different iterations of the search algorithm. The second part of the algorithm simply iterates over the set of all cycles that are found in the first part, and tries to construct a path that starts from the initial state and leads to that cycle. Once the path is found, a complete anomaly is constructed, which can be interpreted as a serializability anomaly and returned to be used for the replaying for the replaying stage of the CLOTHO. Interestingly, in our experiments with this search algorithm, we realized that many of the anomalies constructed by this algorithm can be are structurally similar, meaning that the same transaction instances and the same dependency edges comprise the cycle that is found. For example, all these cycles, even though they are different, but they share the same cycle. In order to exploit this observation, we added an inner loop in the middle of the first part of the search algorithm that once a cycle is found, tries to find all structurally similar cycles to that one cycle. It was interesting that using this simple inner loop, we were able to find twice as many anomalies compared to the in benchmarks that we applied CLOTHO on, compared to the basic version. So in order to evaluate applicability of CLOTHO, we picked 7 benchmarks from OLTP Bench project, which is a project specifically designed to, which designs application benchmarks with various properties and complexities. It was applicable on all of them. We were able to find an serializability anomaly in 5 of them, many serializability anomalies in 5 of them. And that was the first set of results. For the second part, we wanted to answer 2 questions. First, are serializability anomalies objectively good notions of bugs? And if so, how does CLOTHO perform compared to a random, undirected testing approach? In order to do this, we created a state-of-the-art random testing framework based on Jepsen, which is a very famous testing framework, which creates a number of concurrently running workers, spawning transactions according to workloads specified in OLTP Bench project, and running them against a cluster of Cassandra nodes running in AWS. And for the benchmark in this step, we chose TPCC, which is one of the de facto benchmarks to be used for any database-related project, which also comes with a set of application-level invariants. These application-level invariants, according to the specification, must be preserved by any valid execution of any valid database. And if they are violated, they are objective notions of good bugs. So and also we added a bunch of additional invariants of our own as well, and we made sure that they must also be preserved by any valid execution of the program. using the random testing tool, we were able to only violate 67% of these bugs, meaning that 1/3 of these bugs could be assumed to be not happening even in a weakly consistent setting, which, however, once we applied CLOTHO on the same benchmark, we were able to construct scenarios based on the set of serializability anomalies that it reported, violating every single one of those anomalies. So the application was not safe. Those invariants were, in fact, being broken in the weakly consistent system that they were being tested on. So that, and by the way, also only 3 of the serializability anomalies that we found we were not able to map only 3 of the serializability anomalies to an invariant, to a broken invariant, meaning that most of them are in fact interesting bugs that should be considered and analyzed. So to summarize, in this paper we presented CLOTHO, an end-to-end automated testing framework, which is based on which reduces the problem of finding serializability anomaly to finding satisfying assignments to an FOL formula. We evaluated CLOTHO by applying it on many benchmarks, and also showed that it outperforms a state-of-the-art random testing tool. Yeah, thank you.
Questions? Can we also get the next speaker to come up, please? So I have a question about scalability.
Sure.
Could you talk about that a little bit, as far as how big a sort of like database programs that you can handle with this?
So the scalability, it's interesting. It does not. It is more sensitive to the length of the cycles that we are looking for. You can have, based on my experiments, you can have many transactions or large transactions in the database without affecting the performance or the time that is required to find the anomalies. But the larger that you make that bound, it turns out to be requiring more time. However, we have noticed, and people have noticed, that the minimal bounds that are about 5 or 6, which we have been able to cover in CLOTHO on these benchmarks, is usually enough to find core anomalies, which are the most dangerous ones that must be considered.
Nice.
Yeah.
Any other questions?
So just pushing it out a little bit. So when you say 5 or 6 transactions, is that 5 or 6 transactions that are coming from a small number of replicas, or are you also scaling the number of replicas?
I apologize. Would you please repeat?
Yeah. So if you're talking about 5 or 6 transactions, is that 5 or 6 transactions coming from a small number of replicas, or are you also scaling the number of replicas?
What do you mean small number of coming from? So we have a number of database replicas, and we have a workload generator which has concurrently running workers.
Right, but scaling in terms of the number of, like, there could be multiple transactions on 2 replicas, right, that have to happen in some particular way in order to produce a violation, versus 5 transactions across 5 replicas that require 3 different network partitions before you see a problem.
So what's the question?
Do you scale in that direction also?
In the random.
Number of replicas and number of partitions.
So in the random testing, I was able to increase it as many as I wanted to. I think I chose three database nodes and 1 worker node. That's what I did, but I didn't see anything that would prevent me from scaling it further.
Thank you very much.
Thanks.
We should get back to
Oh, sorry.
microphone.
I like it. Okay. How can I project this onto that screen? That's not that screen. So. I see. Okay, good.
our next